computers really don't understand words like we do, right? So if I type "I love programming" as a written over here, the computer doesn't literally see the meaning of "I love" and programming. At the lowest level, an AI model has to work with numbers. So somehow we need to go from words to numbers to mathematical representations to meanings. And that's exactly what we're going to understand in this video. We're going to talk about tokens, tokenizations, token IDs, vectors, embeddings, and semantic meanings. And finally, how things like vector databases and ChromaDB use all of this. Don't worry if the words sound complicated. By the end of this video, they should all feel pretty simple. So we're going to go from text to tokens to token IDs to vectors. So as you can see, text, tokens, token IDs, vectors to the model. So let's go ahead and get started. Okay, so what is a token? Let's start with tokens. A token is basically a small piece of text that an AI model processes. And one important thing to understand is a token is not always a word. For example, imagine I write "I love programming," right? A tokenizer might break the sentence into pieces like "I love programming." Those pieces are called tokens, right? So now sometimes an entire word can be one token, but other times, especially with longer unusual words, a word can be broken into multiple tokens. For example, imagine the word unbelievable, right? A tokenizer could potentially break that into something like unbelievable, right? So I'm simplifying the exact split here because different AI models use different tokenizers. But the important idea is AI doesn't necessarily read text one word at a time. It reads text in tokens. So now in the next section, let's go ahead and talk about why do we need tokens. Alright, so now let's go ahead and talk about why do we need tokens. You might be wondering, why not just make every word one token? The problem is that language is huge. Think about the words play, playing, played, player, and playground. They all share similar pieces, right? So if every possible word needed its own completely separate entry, the vocabulary would become enormous. And then we also have names, new products, programming terminology, slang, misspellings, different languages, and words that haven't been invented yet. So tokenization gives an AI a flexible way of representing text using reusable pieces, right? So this lets an AI model handle a massive amount of language without needing one unique entry for every possible word. So the process of turning text into tokens is called tokenization, and the program that performs this process is called a tokenizer, right? So imagine we have "I love AI." The sentence goes into a tokenizer, so the tokenizer splits it into "I love AI." Now we have tokens, but there's still a problem. A neural network doesn't want strings like love or AI. It needs numbers. So the next step is to convert each token into a number. And we do that with token IDs. So in the next section, let's go ahead and talk about token IDs. Alright, so now let's go ahead and talk about token IDs, right? So every token in the tokenizer's vocabulary gets assigned a number. So this number is called a token ID, right? So let's use completely made up numbers. So imagine, let's say I, right? It has the token 40, and love has the token ID, say 3021, and so on. Programming has this and all that. So I love this could become 40, 30, 21, and then 8, 9, 12, right? So now we're finally dealing with numbers, but here's something extremely important, right? So these numbers don't actually represent meaning. So 3021 doesn't mathematically mean love, right? So it's basically just an identifier, right? So it's an identifier. So think about student IDs, right? So John is maybe, say, student number 100, and Sarah is student number 101, and David is student number 102. So Sarah isn't more similar to John just because 101 is close to 100. The numbers are simply just labels, right? So token IDs work in a similar way. So token ID is equal to identifier, not a meaning, right? So if token IDs aren't meaning, how does the AI represent meaning? That's where vectors come in. So in the next section, let's go ahead and talk about vectors. So now let's go ahead and talk about vectors, right? So first let's start with what is a vector? So right, so the word vector sounds like very mathematical, right? But the basic idea is surprisingly simple. A vector is basically a list of numbers, right? So for example, point 0.2, 0.7, or like as you can see here, 0 0.4, 0 0.2. This is a two-dimensional vector. So now this 0 0.4, 0 0.9, this is a four-dimensional vector, right? So and this is an AI vector. So a vector is basically just a list of numbers. So if it has four numbers, it would be called a four-dimensional vector, as you can see here, right? So if it has two numbers, it's called a two-dimensional vector. So real AI vectors can contain hundreds or even thousands of numbers, like for example 0.021, 0.482, 313, and so on. So like now why would we want a giant list of random looking numbers? Because vectors give AI a way to represent relationships mathematically. Okay, so now this brings us to one of the most important words in AI, embedding. So an embedding is basically a vector representation of information. So for example, if we have dog over here, it could be converted into a vector of puppy, right? Or cat, right? Or and because dog and puppy or dog and cat have similar meanings, their vectors should generally be close to each other, right? So for example, if we have dog or and puppy, so dog could go to the embedding model, and the embedding model creates the list 0.23, 0.81, 0.47, and then it becomes puppy, and then we have the vector for puppy, right? So these numbers aren't manually created by a programmer, right? So a trained neural network called an embedding model produces them. So the pipeline looks like this: text, embedding model, vector, and embedding, right? So for example, if we have I love programming, that becomes 0.18, 0.7, 0.39, and so on. Now that sentence has a mathematical representation, right? Now let's go ahead and talk about semantics in the next section. Alright, so you'll constantly hear the word semantic, right? So semantics simply means meaning. So let's look at two sentences. So here's sentence one. I bought a car. So now sentence two is I purchased a vehicle, as you can see right over here, right? So they don't contain exactly the same words. So bought is different from purchased, car is different from vehicle. The humans immediately understand that those sentences have similar meanings. That is semantic similarity, right? So I bought a car will be equal to I purchased a vehicle. Different words, but similar meaning. This is where embeddings become extremely useful, right? So an embedding model can convert both sentences into vectors. And if the model is good, those vectors should be relatively close, right? So all right, now let's talk about how we can compare two vectors. So if we have two vectors, how do we know whether they're close or similar? There are different mathematical techniques, but one extremely common method is cosine similarity. So you don't need to memorize the math here, right? So the basic idea is that we're checking how similarly two vectors are pointing. So if they have similar directions, they're similar. So for example, if we ask it, how do I change my password? And then how can I reset my login password? Would probably have high semantic similarity, right? So here, reset my password is vector A and change my password is vector B. So they both have high similarity. But now, if we have, as you can see over here, best pizza recipe, this would have a much lower similarity, right? This allows us to search based on meaning instead of exact words. So let's go ahead and move on to the next section. Right, so now let's talk about semantic search. So imagine a document says employees receive 20 paid vacation days each year, right? And the user searches how much annual leave do staff get. So the wording, as you can see here, is different, but the meanings are close, right? So a keyword system would struggle heavily because so employees and staff, it wouldn't recognize employees and staff, right? And leave and vacation, a keyword system would not be able to recognize those, right? But semantically, leave and vacation are related. Also, semantically, employees and staff are related. So vector search can recognize that these sentences mean similar things, right? So this is known as semantic search. So instead of asking, do these sentences contain the same words, we ask, do these sentences have similar meanings? So this is how semantic search works. And The search process is question, and then we get the embedded query, the query vector, and the vector search, and then we find the closest chunk, and then we return the text. So next, let's go ahead and talk about vector databases. Okay, so now imagine you have a million documents. Each document or each small piece of document can be converted into embedding. So now you have 1 million pieces of text and 1 million vectors. We need somewhere to store these vectors, and more importantly, we need a fast way to search them. That's where a vector database comes in. A vector database is designed to store vectors and find similar vectors efficiently. So examples of vector databases include ChromaDB, Pinecone, Quadrant, Waveit, and Milvus. And many traditional databases now also support vector search. So, and the most famous one is actually ChromaDB because it's mainly used in a lot of AI projects and so much stuff. So now, in the next section, let's go ahead and talk about RAG or Retrieval Augmented Generation. Alright, so RAG stands for Retrieval Augmented Generation, right? So that sounds complicated, but the basic idea is very simple. Before the AI answers the question, we retrieve useful information, then we give that information to the AI. So first of all, we get the user's question, and then we search documents, and then retrieve relevant information, and then we give that information to the LLM, and then it generates the answer. For example, you might send this to the model. Say, for example, in the documents, our context is that employees receive 25 days of paid vacation per year, and then the user asks the AI a question: How much annual leave do employees get? And now the model can answer: Employees receive 25 days of paid vacation per year. So right, so the model didn't have to memorize that information, right? So it retrieved it from its own documents. So now let's go ahead and move on to the final sections for this video. This is the glossary and the final section for the video. So here's a quick glossary. You can take a screenshot or save if you need anything. So token is a small. So in summary, a token is a small piece of text processed by the model. The tokenizer is the software that splits text into tokens and maps them to IDs. Token ID is the integer label for token in vocabulary. A vector is an ordered list of numbers. An embedding is a learned vector representation of information. And then we have dimension, semantic, which is meaning, how similar two pieces of text are in meaning. It's like the most extremely common way to compare two vectors. Chunk, a smaller piece of a large document. We have a vector database, ChromaDB, and then we have RAG. So this is the final mental model. So this is what happens. It gets tokenized into tokens by a tokenizer, vectors, and all this, and this happens. So yeah, this is actually pretty much it for this video. I hope you guys enjoyed it. If you enjoyed it, make sure to smash a like and subscribe to my channel, and we have a lot more machine learning videos coming up. Thanks for watching.